This is section 3.3, inference for the sample mean. We're going to learn how to do a one sample t-test. So just like with proportions, we learned how to do tests of significance to see if our population proportion was a certain number. Now we can do the exact same thing, but for sample means. So the theory behind it is very similar, but we're going to learn new applets and we're going to learn new formulas. So look at the learning objectives. Let's start with simulations for means. So just like proportions, we can use simulations to see what possible sample means we could get. But simulating possible sample means is more difficult though. You actually have to have the hypothetical population to actually draw the samples from. So if you remember in our last section, we did draw sample means. So for example, let me pull it up in the eyesight applet. We have quantitative one mean. I pulled up my pennies data. Remember this, our pennies was this left skewed data, and I can do 1,000 samples. Each one has a sample size of 10. And I can look at the possible sample means. We're like, oh, they're almost normal, not quite. You can find your mean and SD. We can do all of those things. But this one, we actually had this population data. Most of the time, we only have sample data and we don't have population data. Now, for proportions, it doesn't really matter because it's either like a yes or a no, and you know, like the percentage. For quantitative data, it's completely different. And so it has to have some kind of population to actually draw samples from. So what we're going to do, if we only have sample data, is we actually make a hypothetical or a pretend population. And we can use this using the one mean simulator in the Zybook in section 3.10. So let me show you what this would look like. For our first example, birth weights in the United States follow a normal distribution. Okay, so important to know that's a normal distribution with a mean of 30 to 50 grams and a standard deviation of 550 grams. First of all, is this a population or sample? Well, you'll notice looking at it, it didn't tell me a sample size. It didn't say, like, it didn't have the word sample in there at all. It kind of sounds like it's saying everyone in the United States. So I think this is supposed to be population data that they're giving me. So I think this is the population of all the babies in the US. So then the values they give me must be parameters, population parameters. So I could say things like the mean mu equals 3,250. And my standard deviation, sigma, equals 550. And I'm really bad about it, but you are supposed to add your units, so grams. Now, if I was to sketch the population distribution, this isn't something that we've really been practicing, okay? But it told me that it's normal, so I could draw a normal curve. I know it will be centered at my mean of 3,250. And sometimes we could kind of draw it like this to be like, this is one standard deviation. So we could maybe say like my SD is 550. Not that anything is to scale or anything. It's just telling me, here's my center. I kind of know how far spread apart it is. It's a normal distribution. Now, let's suppose we want to take a sample of 30 babies. Just using the theory, like what should the sampling distribution of possible sample means look like? So we haven't done any simulations yet, just theory. So the shape, well, look at the sample size. So n equals 30 is big enough to guarantee normal for any population. However, we started with a normal population, remember? But population is normal anyways. So for a normal population, then your sampling distribution will be normal for any sample size. So we're definitely going to be normal. Okay, because my population was normal, so the sample size didn't matter, but my sample size of 30 is big enough to guarantee normal anyways. Okay, center. Well, we know that the mean of my x bars should just be equal to my population mean mu, which is 3,250 grams. And my variability, well, we measure that standard deviation. So my standard deviation of the x bars is just equal to sigma over the square root of n. So this is back from our last section. Go back to section 3.2 if you don't remember how to do this. So sigma is 550, and you divide by the square root of the sample size of 30, which gives me 100.41. And sketch it. Mostly, I just want you to compare and contrast the two. So before, we had a standard deviation of 550 for my population. So now, if I was to try and draw what I expect from my different sample means, I'll still be centered at 3250. But now if I want to look at the SD is only going to be 100.41. So we're going to have to be skinnier than the population. We'll have the same center, but we're going to be skinnier because we're talking about sample averages. We have a smaller standard deviation. And remember, this is for all the possible sample means, x bars. So it's not individual values, it's the possible sample means. So now we can actually use the one mean simulator in the Zybook. So let me pull that up. So I apologize, I said section 3.10. I've changed in your notes now. It is section 3.4 because the Zybook lets me change these so it can change from semester to semester. So 3.4, tools, data and formulas. And it's just this first one right here, the one mean simulator. And so you can pick what your population distribution looks like. And we said ours looked like it was normal. You can put in what the population mean is. So it told me that my population mean is 3250. It told me my population standard deviation is 550. Oops. And so I can set the distribution. Now I put in that I want a sample size of 30. Set my sample size. How many samples do you want? Let's say at least like 10,000, which I think is the max it will let me do. Okay, so let's look at what it's giving me. So for my hypothetical population, I started off with a normal curve. You can see the mean and SD. Just double check that's what you meant to put in. Okay. These are my different sample means that I got. You can see how it says means here. You can see the mean of all the means, 3248. That's pretty close to what we were predicting. The SD is 100. That's close to what we were predicting. Okay. Over here, we have just our individual data from one sample. You could click a different, nope, I guess you can, it's just slow. You can click a different point and it will show you the actual data that was in that specific sample for the new point that you're clicking. Okay, so now let's pause for a minute and think about, usually if we went back to the quantitative one mean applet for our ISI applets, it lets you put in different populations, but if you don't have the actual population data, then it doesn't give you anywhere to put in the population info of the mean and SD if you don't actually have the true data. That's why you have to come use this Zybook. So it does make up a hypothetical population, which we're going to talk about in a minute of why that's okay. But then you can see what the different sample means will look like. Okay, so here's what we got. Does the sampling distribution match our theory-based predictions? Again, it looks normal. Our means and SDs line up. Yes, everything looks just like what we expected it to. Now, out of curiosity though, what would happen if I hadn't started with a normal distribution? So we can do it again, but we can tell it to do a distribution that's skewed right. So I go back through the exact same process, but my population, I say skewed right, I put in the same mean and standard deviation. So this is my actual population here. So it starts with a different population. Okay, I do a sample size of 30, 10,000 samples, and notice my distribution. It looks almost exactly the same. Okay. Now, sample size of 30, we said that's big enough to guarantee. You'll notice it's still a little bit skewed, but we're okay with that. It's close enough. It's not going to make a big difference in any of our calculations. We're fine. Okay. So these, the shape matches and the mean and SD match. Really, nothing changed, even though we started with a different population, which is really cool. So that means it really doesn't matter what our original population looked like, as long as our sample size is at least 30. The sampling distribution of different sample means will always be normal with the same mean and same standard deviation. And that's why we can use a hypothetical population and not worry that it looks different than the true population. So it doesn't really matter in our population if this looks a little bit different or what our populations look like. As long as your sample size is big enough, your possible sample means looks exactly the same no matter where you start. So what can we do with that? Let's figure out how to actually do the test. So now we have a random sample of 30 babies from a hospital last month with an average birth weight of 3,400 grams and a standard deviation of 635 grams. Is this evidence that this hospital's babies' birth weights average above 3,250 grams? Okay. So we're going to use the one mean simulator again to find an approximate p-value. But first, are these numbers parameters or statistics? So now these are for our sample because it's telling us we have a random sample. So they are statistics. So now I would say things like my sample size is 30, n equals 30. I could say my sample mean equals 3,400, and S, my sample standard deviation, is 635. And what we want to know is is, I actually like to write this out, so I want to say something like, is my population mean greater than 3250? So basically, that's my research question. Sometimes writing out the research question can help me figure out what numbers to put into my applet. So the null hypothesis would be that the population mean is greater than 3250. Or if we want to use symbols, we could say that my population mean mu is greater than 3,250 grams. Sorry. You wouldn't believe it, but when you're trying to talk and write and record at the same time, you say things that you don't mean and you would never actually say. Okay. When I want to know if my population mean is greater than 3250, that is my alternative hypothesis. That is what I'm trying to show. And my null is then the HA is that my population mean is greater than 3250. Sorry, I'm in the habit of writing that first. I just wrote it in the wrong spot. My null hypothesis is always an equals. So my population mean equals 3250. Or if I want to write it in symbols, I do an HO for mu equals 3250 grams. So going back to my applet, okay, we drew all of our samples and everything. Notice it will even tell you that the null hypothesis is that my population mean equals 3250 because that's what I put in for my population mean. So it realizes that's what you want to test with your null hypothesis. Okay. Then you say statistic is means. We're not using medians. We're not going to do that. We're just using means. Our observed statistic, what we actually got in our sample is 3,400. So I type in 3,400. You have to do the direction. So we want a greater than or equal to was what we were picking and compute. It will shade in the values in the tail here. It did everything greater than 3,400. It doesn't put the p-value up there, but it does come down here and tells you there were 691 that were greater than that 3,400, if you really cared, but it doesn't really matter to you. You can see the mean and standard deviation of the sampling distribution. Again, those numbers were also written in the graph. Okay. But now it gives you a p-value. So my p-value is 0.069. And it tells you your standardized statistic. Now, it's writing a t here, and we're going to talk about why in a minute, but for now, just think of it as your normal standardized statistic, 1.494. So my p-value is 0.069. Now, you might notice this is slightly different than what we just barely got, okay? Because it's a simulation, so simulations are always a little bit different. Let's go with what's written down on your notes. So you can find your p-value and your standardized statistic here. So my p-value is 0.071. And my standardized statistic, t equals 1.491. It means the same thing as what we learned before, and we'll talk about why it's suddenly a t. Okay. Now looking at both of those, we know things like if my p-value is smaller than 0.05, we will say that we have evidence against the null, that my null is not plausible. But this p-value is actually kind of big. That's bigger than 0.05, right? So we could say, like, that's a big p-value. And then that means that the null is plausible. And so that means no evidence for the alternative. Okay, same thing for the standardized statistic. So t equals 1.491 is less than 2. That's the cutoff for standardized statistics. So the null is plausible. And so either way you look at it, I think we could tell our boss something like, let me type. We did not find evidence that the average birth weight of all the babies, because it's about my population, not my sample, is greater than 3,250 grams. So basically, they're like, hey, our sample of 3,400 was bigger than 3,250, We're like, maybe our hospital is special. Okay. But when we looked at it, we're like, oh, no, that was probably just chance error. That was probably just which sample you picked. That wouldn't have been surprising. It's still very plausible that the mean is 30 to 50. And I did say the average birth weight of all the babies, but this was a sample just from our hospital, so it's all the babies at this hospital. Not from the entire US, just this hospital. Now, could we do a theory-based test? Yes, just like with proportions. If our sample size is big enough, at least 30, we can use theory-based formulas and the normal curve to find p-values. So using the applet, we just check the theory-based approximation option. So I just come back up here, theory-based right there, click it. Now it turns orange. Oh, I disappeared. Sorry. Okay, so now it's telling you it's using a t-distribution. We'll talk about that. It tells you the theoretical mean and SD. Notice my simulated values were very close to my theory values. It tells you a p-value and a standardized statistic. Again, very close for a simulation or theory-based. So you can see I put it on here. These are your theory-based values right here, the p-value and the standardized statistic. So my p-value is 0.073. And t equals 1.494. Again, we'll have the exact same conclusions as what we just found. We don't need to write it down again. But you can see that's how you do the simulation. This is how you do the theory-based approach. But now, here's the wrench for sample means. What if we don't know the population standard deviation sigma? So in the baby weights example, we actually made up that population standard deviation of 550 grams. In practice, we're almost never given the standard deviation of the entire population. So what can we do if we don't know the population standard deviation sigma? So for like this example, the other professor, they pulled it off of the CDC website what the average weight of all babies was, but they looked and couldn't find anything that told them the population standard deviation. Like people just don't report that very often. Okay. So what if we don't know the population standard deviation, or we don't know any information about the population anyways? Like we can't tell you the standard deviation if we don't have all the population data. So what do? If we don't know the population standard deviation sigma, we estimate it with the sample standard deviation S. But we know that the sample standard deviation will never be exactly the same as the population standard deviation, just like our sample means aren't exactly the same as our population means. So we're introducing more uncertainty into our calculations. So to compensate for that extra uncertainty, instead of using a standard normal curve, we use what's called a t-curve. The t-curve looks like a normal curve, but it's a little bit flatter and it has extra area in the tails. And it has something called degrees of freedom, df, that change the shape based on the sample size. So for example, this black, solid black, is the t-curve with 1 degree of freedom. And the dash is my normal curve. So you can see the t-curve is a bit flatter because it has this area out in the tails. It has more area out in the tails. That's for 1 degree of freedom. By the time I get to 10 degrees of freedom though, my t-curve still has a little bit more area in the tails, but you don't notice it very much. By the time I get to 30 degrees of freedom, you can't even tell the difference. So let's look at this applet. Well, this is one that I made. You can see the red is the t-curve, the blue is the normal curve. So when we start at 1 degree of freedom, there's a very big difference. You can see all this extra area. But then I can just drag this degrees of freedom and just watch what happens to that red curve. As I drag it along at 3 degrees of freedom, it's closer. 5, we're closer. 7, 9. As I drag it along, we get closer and closer and closer and closer to that normal curve. And if I get big enough, you can't even tell the difference. So we like the t-curve. It compensates for that extra uncertainty when you have small sample sizes. By the time you get a big enough sample size, it doesn't even make a difference anymore. You could have just used the normal curve. Okay, but we use the t-curve when we don't know the population standard deviation because it just has a little bit extra area in the tails. So back to our baby weights. We were told the population average is 30 to 50, but we only have the sample standard deviation of 6, S equals 635. So if we want to take a sample of 30 babies, what would you expect from the sampling distribution of the possible sample means? Okay. So, I mean, we looked at this before, but we're just going to change a little bit of the standard deviation. But to start with, our shape is going to be normal because my sample size of n equals 30 is big enough. It's bigger than 30. Oh, also population is normal. Now my center, so the mean of all of my x bars is just equal to mu, so 3250. And my spread, my SD of my x bars is, well, we don't actually know it. So it's supposed to be sigma over the square root of n. Okay, but we don't know sigma, so what are we going to do? We're going to have to approximate it with s over the square root of n. So when I do my sample standard deviation of 635 and divide by the square root of 30, I get 115.9. So this is different than what we got before because now we're using our sample standard deviation to estimate it. When we have to use our sample standard deviation instead, this is now called our standard error. We just like to make up new terms in statistics. Okay, so when we estimate the standard deviation of the null distribution using our S, our sample standard deviation, we call it the standard error. So basically, if you know the population standard deviation sigma, then you can say the SD of all the x bars is sigma over the square root of n. But if you have to estimate it using our sample standard deviation S, now it's called the standard error of all the x bars, and it's standard error SE equals S over square root of n. Same concept, we're just having to use our sample standard deviation. So now that we've learned all of that, okay, let's talk about how to use our theory-based one sample t-test. Basically, because we talked about how you have to have a hypothetical population to draw our samples, we're actually not going to use simulation a lot for our means. We're just going to use the theory-based one sample t-test. So in your homework, we might have you do a few simulations just for practice and to understand what's happening. But really on the test, it's just going to be the one sample t-test because it just works better for means. Okay, so the theory-based t-test uses a t-curve to find p-values. So instead of a normal curve or a z-curve, it uses a t-curve. It has a standardized statistic. So remember before our standardized statistics, where z equals our statistic minus the mean of the null distribution over the SD of the null distribution. So that's what we've always been using. Well, when we wrote this formula, okay, they're like, oh, well, instead of saying statistic, we can just say sample mean because we know that's what we're using. Minus the mean of the null distribution, but because we don't know our population standard deviation, we don't have the SD of the null distribution, so we have the standard error, so you have to use that standard error. Or you might see it written out as like x bar, our sample mean, minus the mean of the null over S over square root of n, because S over square root of n is that standard error. Let's see, so our validity conditions, we need a symmetric population, okay? Or, so remember our essential limit theorem, we said if you start with the normal curve, then your distribution will be normal for any sample size. So it's taking that into account. So it's saying a symmetric population, or it's saying your sample size is at least 20 and the sample isn't too skewed. So remember, we said once you get to sample size of 30, you're guaranteed to be normal. But do you remember how we looked at it? And sometimes we had a sample size of like 15 and it still looked pretty normal, or even like 10 and it looked pretty normal. So our textbook said if your sample size is at least 20 and the sample isn't too skewed, so it's at least like almost symmetric, then the t-test still ends up working well enough. Okay, so they gave us a new rule for the t-test, which is that n needs to be at least 20 and the sample isn't too skewed. Now really, if your sample size is at least 30, it doesn't matter what shape the data is. But this is what you need to memorize for the test because that's what they put in the textbooks. Okay. And the conclusion, well, if your p-value is less than 0.05 or your standardized statistic t is greater than 2. Let's look at this picture that I have for. So this is my standardized statistic t. If you're less than -2 or greater than +2, then your null is not plausible. That means you have evidence for the alternative. But if you have a t-value that's in the middle, then your null is plausible. Or if we're out here in the tails, we can say like my p-value is less than 0.05, or over in this tail, like if my p-value is less than 0.05. So if you're far out enough in the tails, so your p-value is less than 0.05, or your standardized statistic is above 2 or less than -2, then your null is not plausible. If you're in the middle, then your null is plausible and you don't have evidence for the alternative. And we're going to use the ISI applets. It's called theory-based and one mean. So let's try it with our baby weight example. still. So we've already found our hypotheses and everything. Let's see, are our validity conditions met to use the theory-based approach? Well, we started with normal population. So, yep. Also, my sample size is over 20, so that would have worked as well. So let's go to our theory-based applet. We haven't used this one yet. So you go to your applets. It's under Calculators Theory-Based Inference. You have to change the scenario from one proportion to one mean. Then you put in your sample data. So in this spot, everything we put in here is our sample data. So my sample size is 30. My sample mean is 3,400. Biggest problem is to make sure you don't mix up your means. My sample standard deviation is 635. Calculate. And then you have to come over here to where it says options. So this is trying to do something called a confidence interval, which you haven't learned how to do yet. So now you click test of significance. You have to tell it what your null hypothesis is. So my null hypothesis was we're testing to see is it 3250 or is it above that. So you put in the 3250 for the null hypothesis. It will fill that in for the alternative. You have to pick which way we're looking for above. So it's greater than. And then it gives you all of these results, which you can see here on the notes. So you have to come way down. Notice these are my possible sample means. You can see the mean and SC of all my possible sample means. It put on my t-scale for you, so you can see that my t-value is something less than 2. But specifically, my standardized statistic, t is 1.29. I have 29 degrees of freedom. Remember, that's just something that changes the shape force based on our sample size. And my p-value is 0.1030. So my p-value, I think I said 0.1030. So that's a big p-value. So the null is plausible. No evidence for the alternative. Let's try our standardized statistic though. If you go back down, my standardized statistic is that t-value 1.29. So t equals 1.29. That is less than 2. Because remember, we're trying to say, like, here's 2, here's negative 2. And if we're at 1.29, that means we're in the middle. So that means the null is plausible. Not that you have to do that. You can always just use the p-value, but so that you understand it if we ever ask you. Okay. So now that we've done all that, let's write out what is our actual conclusion. I would say something like, we did not find evidence that the average birth weight of all babies at this hospital is greater than the 30 to 50 grams. You'll notice these values are slightly different than when we did it before because now we're actually using our sample standard deviation instead of that made-up population standard deviation. Now there's something we haven't actually talked about yet, which is errors. So if we're using significance tests to determine if the null is plausible, we can get the correct decision, or we can actually conclude something that isn't true. Like, we don't like that, but we realize we're just looking for evidence, we can often be wrong. So this is a little matrix here. If you can think about as the truth is either that the null is true, or the truth is the null is false. There's only two options really, like either your null is true or the null isn't true. Now, what can your conclusion be? So if you conclude that you have a small p-value, you're going to think the null is not plausible, and you're going to say you have evidence for the alternative. So if we look at this, if the truth is that the null is true, but we decide that the null is not plausible, we've made an error. That's called a type 1 error. Okay? But now if the null is actually false, and we decide that the null is not plausible, or we're saying the null is false, that was the correct decision. Okay. Now let's say we got a big p-value. So we're thinking the null is plausible, no evidence for the alternative. So if the null is true, and I decide that the null is plausible, I made a correct decision. But now let's say the null is false, but we got a big p-value. So the null is false, but I think it's plausible I made a mistake. That's called a type 2 error. So we're going to do some examples to try and help us remember what type is what, because it does come up on the test. You do have to be able to figure out what type of error was made. So let's imagine a person going to the doctor. The null or nothing exciting hypothesis should be that they're not pregnant. So forgive me, I really proofread these so many times. Okay, the null is that you are not pregnant. Okay, that's the status quo. Most people throughout most of their life are not pregnant. That's the status quo. The alternative then is that you are pregnant. So if you think about it, there are two options. Either you're pregnant or you're not. Okay, as far as the truth, pregnant or not pregnant. But there's two decisions we can make. Okay, so if we get a small p-value, that means the null is not plausible. So it's no longer plausible that you're not pregnant. So we have evidence for the alternative. We have evidence that you're pregnant, and we conclude that you're pregnant. So if you're really pregnant and we conclude that you're pregnant, that would be, oh, sorry, I've got to, okay. To make it match up above, let's say, just rewrite these, I'll fix it on your notes. So the truth for the first one is not pregnant. Truth for the next one is pregnant. Okay, so if the truth is that you're not pregnant, but you decide you're pregnant, well, that would be an error. Specifically, this is what we call a type 1 error. So type 1 error always goes with small p-value. So small p-value, if you make a mistake, means it's type 1. Big p-values, if you make a mistake, is going to be type 2. Okay, if you decide that you're pregnant and you actually are pregnant, then you are correct. Congratulations. We're hoping that happens most of the time, that you're correct most of the time. But now, let's say that you got a big p-value. So you think the null is plausible, that you're not pregnant. There's not evidence for the alternative, and you conclude that you're probably not pregnant. Okay, so we decide you're not pregnant, and the truth is that you are not pregnant. So that means you were correct. We always like it when we're correct. Okay, but now, if the truth was that you are pregnant and you decide that you're not pregnant, that's a type 2 error. So the way I always remember it, small p-values is always going to be a type 1 error if you make a mistake. Big p-values are always a type 2 error. Okay, so here's a little picture to help you remember this forever, hopefully. Type 1 error is you're actually not pregnant. So you're actually not pregnant, but you decide you're pregnant. Okay, so, and really, I know these are so easy to think yourselves in circles. So type 1 error means not pregnant, but you decide you are. A type 2 error then is you actually think you're not, but you are. So you are pregnant, but think you're not. Okay, let's try a few other examples. So baby weights, back to our example of the baby weights we spent so much time on. Based on our simulated and theory-based approaches, we decided the null is plausible, that all the babies in the hospital could have an average weight of 3250. Remember, we had a big p-value. So in other words, we didn't have any evidence that their average weight is greater than 3250. But now suppose someone actually collected all the data for all the babies at this hospital, and it turned out that the average weight actually was greater than 3250. So we had a big p-value. We thought null is plausible. Okay, but when they actually collected the data, the null is wrong. Okay, so what type of error do we make? Big p-value always means type 2 error. Let's see, suppose you did a study to see if the mean amount of time that USU students spend watching TV was less than 4 hours a day. You got a p-value of 0.03, so that's a small p-value. And so if we get a small p-value, we're going to say the null is not plausible. Okay, and so we think that my population mean is greater than 4 hours. But then let's suppose that some all-knowing spy, like Google or something, collected data and told you the true hour average is actually 4 hours a day, and you had just gotten unlucky in which sample you picked. So what type of error did you make? So again, we had a small p-value, but we made a mistake, so that's type 1. So let's see. We thought that it was greater than 4 hours. It actually is 4 hours. So actually the null is true. Okay. We made a type 1 error. These are just a few different mnemonics, so you can hopefully find one that works for you. So apparently a common one is the boy who cried wolf. So in the story, the villagers make the two types of errors in order. So the null hypothesis is that there's no wolf. That's the status quo, dull, nothing exciting is happening. The alternative is that there is a wolf. Okay. So first in this story, he cried, there is a wolf, there's a wolf. So they thought that there was a wolf. Okay. This would be like a small p-value. They're rejecting the null. They think there is a wolf. Okay, so they reject the null falsely. Okay. But then the wolf actually did come and he cried wolf, wolf, but no one believed him. So people said, no, the null is true. They had a big p-value and they thought that the null was true, but it actually wasn't. Okay, so when we make a type 1 error, it's often called a false positive. They thought there was a wolf. It was positive, like positive, yes, there's a wolf, but it was false. And a false negative is when something's actually there, but you think it's not. So you'll see that terminology used a lot in practice. Okay, but really, to remember the difference, I always think of it as we're always hoping to get a small p-value. When you get a small p-value and make a mistake, it's a type 1 error. So I always remember it's type 1 because we put what we're hoping for first. So since I know I'm always hoping for a small p-value, I remember that's the first thing. That's a type 1 error. Okay. One more example. According to a 2018 report by the U.S. Department of Labor, Americans spend 2.84 hours per day watching television. Suppose we take a random sample of 100 USU students to see if students at USU watch less TV than the national average. Suppose the sample gives us an average of 2.2 hours and an SC of 1.5 hours. So what is the population we're actually interested in? So it's not actually all Americans. We're only looking at students at USU. So the population would be all USU students. The parameter would be the average TV of all USU students. We'd use the symbol mu, and do we know what that is? We don't actually know what that is. We want to do a test to see if it's less than 2.84 hours, but we don't actually know what it is. Okay, my sample is the average TV of the 100 USU students. And my statistic then, my sample is just the 100 USU students. And then my statistic is the average, or the mean TV of the 100 USU students. And we can say that's X bar equals 2.2 hours. And we should also write down, so we had X bar equals 2.2. We should also note that my sample standard deviation equals 1.5, and it'd be useful to write down my sample size of 100. And I always like to write down my research question. What's my research question? It was, is my population mean mu? We want to see if they watch less TV than average, so less than 2.84. That's my research question. Now, for the sampling distribution of all the possible sample means, predict the shape. Okay, well, n is greater than 30, so normal. Now, just as a thought, could you predict what the population distribution looked like? I bet the population is right skewed. Okay, because some students will watch more or less. It probably actually looks a bit like this. Some students watch less, a lot kind of watch in the middle, and some students watch a lot. So I bet it's very skewed. But anyways, my sample is bigger than 30, so we know it's going to be normal. My center is just going to be equal to my hypothesized population mean. So let's say for the sampling distribution of all possible sample means, predict it all if the null is true. So my center, or the mean of all of my X bars, is just equal to my population mean mu, which if the null is true, is going to be this 2.84. My spread, well, did anywhere it tell me my population standard deviation? It didn't say anything about population standard deviations anywhere. So I'm going to actually have to use my sample standard deviation. So the standard error is just going to be S over the square root of N. I can't do sigma because I don't know sigma. So instead it's the standard error. And we're estimating it because we have to estimate our sample standard deviation. So it's just going to be 1.5 over the square root of 100, which should give me 0.15. Now we can use the theory-based applet to actually test our research question. So remember, our alternative, what we're hoping to show is that the population average is less than 2.84, which means my null would have to be that my population average equals 2.84. If I want to use my symbols, this would be HO, that my population mean mu equals 2.84. And the alternative then is that my population mean mu is less than 2.84. Now for my standardized statistic, you can always just pull this off the applet, but I want to show you that you could get the answer by doing it by hand. So my statistic, the number I actually got is my sample average, so 2.2. So my statistic or my sample average is 2.2 minus the mean of my null distribution of 2.84 divided by my standard error, which we just said is 0.15. So that should give you negative 4.27. Now, again, in this class, we're going to show you how to do a lot of things and the background behind a lot of these things. But really for the test, you only have to be able to use the applets usually, and you can pull almost everything off of the applet. But we show you how this happens so that you don't think the applet is just magic and you don't understand what's happening. So I pull up my applet. If you remember, in the ISI applets, you want to go to calculators, theory-based inference. Okay, scenario you have to change to one mean. Put in your sample data. So I think my sample size is 100. My sample mean is 2.2. And my sample standard deviation is 1.5. You click calculate. Okay, this you don't know what it is yet, so just go to test of significance. You have to put in what the null hypothesis is of 2.84. You have to click which way the arrow should go. So we decided we're trying to show this less than. And now it will show you, like, this is the null distribution of all the different possible sample means. Here's the theoretical mean in SD. It will show you what your test statistic is and degrees of freedom and a p-value. But you can also see here. So this is my standardized statistic. This is my p-value. So my p-value is almost 0, which is a small p-value. Also, my test statistic is more than 2, like less than negative 2. It's out in the tails farther than 2. So my null is not plausible. So I have evidence for the alternative. So we can say we have evidence that the average for all the USU students is less than 2.84 hours. Of course, that's made up. Maybe we watch more than the average. I don't know. Now, it turns out that the amount of time watching TV is very right skewed. Can we still use the theory-based test with our sample of 100? So even if we start something very right skewed, can we still use a theory-based test? Well, the theory-based test just says that you need N is at least 20 and not too skewed. Is the one that the book wants you to memorize, or really need N of at least 30 for any population. So could I use a theory-based test with a sample size of 100? Well, that's bigger than 20. Of course, it was pretty skewed, but it's still bigger than 30, so yes. Okay. Could we have used it with a sample size of 10? Well, it's pretty skewed, and it's not even 20, so no, you'd have to use a simulation. So you'd have to go into the simulation and do a hypothetical population, but that doesn't really work. for small sample sizes, and so there's actually other things that we can do, but not things that we're going to learn in this class. So in this class, if you're using means and your sample size isn't big enough, it's just going to be something we can't really do. Okay. Now, in this problem, we found a small p-value, but what if our decision was wrong? What type of error is that? So remember, small p-value is always going to be type 1 because we're always hoping for small p-values, so that's our type 1 error.